Kirchhoff's circuit laws are two equalities that deal with the current and potential difference or voltage in electrical circuits. Described in 1845 by German physicist Gustav Kirchhoff. Interestingly, this year corresponds to the 200th birth anniversary of Kirchhoff. According to Kirchhoff's current law, total current entering a junction in an electrical circuit is equal to the total current leaving the junction. Kirchhoff's current law is also known as Kirchhoff's first law or junction rule. It is based on the conservation of charge principle, which states that electricity is neither created nor destroyed as it flows through a circuit. Kirchhoff's current law is considered while designing and analyzing circuits, troubleshooting and repairing circuits. If currents entering a node is assigned positive values and that exiting it negative values, according to Kirchhoff's current law, the algebraic sum of all currents entering and exiting the node will be zero. It is the basis of most circuit simulation softwares and is used along with Ohm's law to perform nodal analysis. Nodal analysis, also known as node voltage analysis or branch current method, is a method of determining the potential difference between nodes, which are points where elements or branches connect to an electrical circuit. An important limitation is that it is not applicable in high frequency alternating current circuits. Capacitive coupling of electric field can occur between the wires of a transmission line. Kirchhoff's voltage law, also known as Kirchhoff's second law or Kirchhoff's loop rule, mentions that the sum of all voltages or potential differences around a closed loop is equal to zero. This means that sum of all individual voltage drops in a closed circuit will be equal to the voltage applied or supply voltage. In such a loop, the current path does not encounter a node more than once. Circuits having multiple loops can be analyzed by applying Kirchhoff's voltage law to each of the loops. Kirchhoff's voltage law follows the principle of conservation of energy. The loops can be traced in clockwise or counterclockwise direction. As the induced electric field produced by an inductor may not be confined to an inductor, leaked fields can cause error in calculation with high frequency alternating current circuits. Now we will use a simple circuit with 3 resistors and a battery to check the Kirchhoff's voltage law. 3 1 kilo ohm resistors have been connected in series to a 9 volt power supply, that is exactly measuring plus 9.32 volts, and we will see what happens at each resistor level. This is the drop of voltage across the first 1 kilo ohm resistor. You can see that it is minus 3.13 volts. This is the voltage drop across the second 1 kilo ohm resistor, minus 3.11 volts. You can see here in the multimeter. This is the voltage drop across the third 1 kilo ohm resistor. You can see that it is minus 3.08. So sum will be almost equal to the 9 voltage power supply. So adding the negative voltages or potential differences and the positive supply voltage, the sum will be, algebraic sum will be 0. Now I have changed the second resistor from 1 kilo ohms to 2.2 kilo ohms. So you can see that the potential difference across the first resistor 1 kilo ohm has come down to 2.21, that is minus 2.21 volts. As expected, the potential difference across the second one is more than double. You can see minus 4.88 volts. That's because same current is flowing through all resistors and with the resistance more than doubled, you will have more than twice the potential difference across it. The third 1 kilo ohm resistor, the potential difference is 2.17. That is almost similar to the first resistor. So if you sum all these negative values of potential differences with the positive value of the power supply battery, then again you get almost zero, taking into account the measurement errors possible.